Hello, can you see the screen?
Yes.
Okay. Yeah. Thank you for the introduction, and it's a great pleasure to present some of our recent findings in this webinar. So I really appreciate. So I will cover three or small stories in this this lecture. So I will first describe my overall interest, because I'm not a hardcore polysaccharide chemist. I come from the multidisciplinary field, and this perhaps a little bit explains why my approach is perhaps a little bit different than very many of these polysaccharide people. I will first describe strain hardening in polysaccharides. So the reason why I will address this is that strain hardening is a relevant function in living organisms. And if we want to make biomimetic materials which mimic in a very honest way the biological materials, we need to understand strain hardening as a material property. And it also gives fault tolerance to the materials, which is also in the relation of material science. It is a very desirable property. Then I will a little bit describe on optical properties of polysaccharides. I will describe whiteness. So why whiteness is topical now? Because quite recently, there has been a European legislation that the white paints related to titanium dioxide or metal oxides are now classified as toxic. And there's a strong search to understand whether there could be other ways of providing white pigments and white colorings. And I will show how strong whiteness can be achieved in nanocelluloses using a specific property which is so-called anomalous diffusion. Then I will also describe a little bit how such strong whiteness properties could be switchable by temperature. And that could be interesting for functional responsive materials. And then finally, I'm going to describe optical fibers based on polysaccharides and why they could be interesting for new applications in textiles, sensors, and also for the medical field. So first, I just showed the general topics where I have been working over the years. I very much appreciate natural materials and approaches because I find hierarchical self-assembly extremely powerful and interesting for making functional materials. And the logic there is that each functionalities requires a certain length scale. And if we want to have multifunctional materials, I think it is very logical to try to combine the different length scales in the single material. And then we could also have switchable properties if we could switch the different length scales, for example, temperature, light, magnetic field, or electric field. Then biomimetic materials are very interesting because usually in synthetic materials, you have the problem that you can either have a strong and stiff material or ductile or tough material, and it is very difficult to combine these properties together. But nature does it, and it does it, for example, in nacre, in silk, and in some other materials. And this is also related to multi-scale hierarchies in the materials. Then, of course, cellulosics, and especially nanocelluloses, is a very interesting group of material. They are colloidal materials, and they have very extraordinary properties. We all know the mechanical properties, but they can be modified with chemically or supramolecularly to have interesting properties. And then, going even more detail in the materials of life, all the living organisms, they are out of equilibrium. They are not, they are driven by energy field, which makes the potential barrier between different states smaller. And this is the biological reason for adaptation, learning, and these kinds of things. And this leads finally to the question that could one do materials which could have some of the most simple forms of learning? Of course, materials don't have soul, they don't have any deeper understanding, but we can make materials which seemingly behave like they would have some logic in their behavior. And I am very convinced that this will provide the next scale of artificial intelligence. We know that artificial intelligence is now made by digital codes, but I think materials can also provide a simplified form of artificial intelligence. Well, let's go now to the three small topics. Strain hardening of polysaccharides and case Agarose. So first, to put the background, the polymer chains can be flexible, semi-flexible, or rigid. And there are two parameters which describe the polymeric behavior in the most crude way. The first is the length of the polymer chain, or contour length of the polymer chain. It's LC. And then there's another parameter, which is so-called persistence length. And this is the length where the polymers forget their local directions. So it means that if this persistence length is short, then it means that the polymer chains tend to make tightly packed coils, like in this case. So if persistence length is smaller than the contour length, then they make tight coils. And these are most of the synthetic polymers are this kind of flexible polymers with flexible chains. And then the thermal energy leads to bending to the coils. Polymer physics says that entropy is the driving force to make them in these kind of tightly packed coils, because in this case, this order is maximized. The other extreme is rigid polymers, like conjugated electroactive polymers, which are almost fully rod-like. We don't address these kinds of polymers here. But what is in between? In between, there are so-called semi-flexible polymers, where the thermal energy does not effectively lead to bending of the polymer chains to coils. So the interactions are there more important than entropy, and therefore it is called enthalpic elasticity. And in fact, most of polysaccharides and biological polymers deal this group of material. And this is the topic of today. So let's see how polymers behave in rheology. A typical rheological experiment is, for example, a cone and plate rheological system. And then the polymer layer is sheared in between the two plates, and one can define what is the stress of the material and what is the strain of the material. And strain means the deformation, or the extent of the deformation. And in classical flexible polymers, the behavior is something like this. Here is the strain or stress, or it means the amount of deformation. And here are the two different moduli which describe the material. So there are two moduli. There's so-called elastic modulus, which describes the stiffness of the material. So it's like a elastic spring constant in spring. And then there's a loss modulus, which describes the viscous losses of the material. And what happens in the classic polymer, it's usually the elastic modulus is higher than the loss moduli, but most importantly, as a function of strain or stress, this moduli value becomes smaller. It means that the polymer chains the coils start to a little bit deform in their shape so that they can flow past each other more easily. So this is exactly the reason that they are the entropic springs. You could think that you can just extend the spring and then it will be more slim. So this is important in some applications. For example, if one would like to have injectable gels in medicine, then this is a very desirable property. So that, let's say, if you have an injection, then it flows easily and then it settles to the tissue in a nice way when it is in a stable state. However, if we take polymers or macromolecules in nature or living organisms, the situation is a little bit different. So here is a deformation, the strain, and here is the modulus value. And here is a synthetic polymer. This is in fact a gel. These describe gels because the natural living polymers tend to make fibrillar networks. But you see that the synthetic polymer in this deformation range, they behave, it's constant, and you don't see upturn there. Unlike, for example, in actin, you see an upturn when you have a high deformation, the modulus value increases. This happens also for collagen, fibrin, vimentin, and neurofilaments. It seems to be a general natural case that as a function of increased deformation, the modulus value become higher. And why is this important? Because think about that this is a biological tissue and you would have a kind of wound here or defect. And then there is a deformation. Then if you have a fixed deformation here, the pressure or the force divided by the surface area here is larger than here. Then it means that there is a tendency for the defect to grow, especially in this part, if in the normal case. But now, if the system becomes more stiff here, then it resists of increasing of this crack, and then it makes the material fault tolerant. And this is exactly the reason that evolution in biology has required that this kind of strain hardening takes place. And if you see what kind of these polymers or macromolecules are, you see that they are not tightly packed coils, but they are more elongated. They make a mesh-like material. And this is the first indication that these biological macromolecules are different. They are not coil-like, but they are semi-flexible. Then comes a question that if you would like to make, for example, in tissue culture materials that would behave something like the natural extracellular matrices, you would like to have materials where the polymer chains behave like semi-rigid or semi-flexible manner. And it has turned to be quite difficult to rationally design these kinds of materials. And there are some efforts in the previous literature. So this is, for example, the Nijmegen group effort, where they have made polyisocyanopeptides where there's a helical polymer backbone, which tends already as such to make a rigid backbone, but there's also hydrogen bonding network around the helical core, which rigidifies the material. And then to make the functionality, for example, tissue culture, they have outer layer brushes there. And indeed, if you see what is the stress here is a stress value, and here is a modulus. Don't care what is now the differential modulus. So there's a certain definition, but this is the modulus. You see that the modulus increases by stress. So there is indeed stress hardening. And then we ask the question, but aren't polysaccharides also biological molecules? Because we know that they are rather rigid. Yes, indeed, they are. But the curious thing is that there's surprisingly little or small literature describing strain hardening in polysaccharides. So here is a selection of them. So one can see strain hardening in pectin, then agar, locust bean gum. Then there was a very recent paper by Buttova and the others for starch. Then we have been working on methylcellulose and also its compound with cellulose nanocrystals and agar. I will still emphasize that yes, indeed, in polysaccharides it seems to be a property, but it is less reported than expected. Then there's another aspect also which is related to this strain hardening, and this is that the junction architecture has to be engineered. So all of these semi-rigid materials make network materials. And if you, for example, see here a junction point, which is the crosslink point, it can be a physical crosslink or just physical or chemical crosslink. So it means that it can be a permanent or exchangeable. It really doesn't matter. But the architecture is important. So how many chains are connected here? Here it is said that the coordination number of this junction point is 4 because there are 4 chains connected. This is called crosslink coordination number, and this is very important also in the engineering. For example, if you want to make a rigid structure based on in engineering, there's a certain number or critical number of coordination which gives a rigid structure. For example, in 2-dimensional, this is if the coordination number is less than 4, the system is not stable. But if it is 4, it starts to be stable. And if it is more than 4 in 2 dimensions, this is of course then stable. And in 3 dimensions, the critical number of coordination number is 6. And this is really not a new thing, because the famous Maxwell studied it 150 years ago. So the critical number of junction coordination number is 2 times the dimensionality. And in biology, evolution has also made rigid structures based on exactly this critical number. But things are not so easy because, so I said already that if one would like to make strain stiffening materials, then one has to have sufficiently rigid chains. We addressed this topic already. And also that we need to have the junction coordination number larger than certain critical value. But the situation is a little bit more complicated, because in this paper, McIntosh and others noticed that if you impose strain to the system, the critical junction coordination number goes down. And then in principle, you could be able to design strain hardening so that in the no deformation case, you have the junction coordination number smaller than the critical value. And then when you deform the system, then it passes over the critical value. And then you could have strain hardening. Here is, for example, electron microscope picture with junction number 3, and here is junction number 4. So in summary, for strain hardening, design semi-rigid networks just below the critical network connectivity, and then you deform. Simple, but it is not so simple to make it rationally. So let's take Agarose. Agarose is a biopolymer which can be taken from nature, from red algae. It's a polysaccharide, and it can form random coils, and then it can also form double helices. At high temperature, it forms these kind of random coils, but let's say lower temperature, it forms double helices. And you can see the double helices even if you carefully look in the AFP pictures. And then it also gels at low temperature. So then we try to see the rheology in this system. Here is strain in the dynamic rheometer, and here is the modulus. Don't pay attention what is this LVR. This is just some scaling, which is not important in the present case. So if we took a normal procedure that we took a sol, which we made at a high temperature, and then we made a cake by cooling, and this is the gel then, and then we insert it in the rheometer, and then we study with the parallel plate geometry. We see this kind of behavior that then modulus drops when you impose strain. It means our conclusion is that it is not strain hardening, it's strain thinning. Well, a general problem in gels is that there's a slippage between the plate and the material, and then one can try to solve the situation having rough plates. Well, then we took exactly the same procedure, but then we, instead of smooth plate, we take a rough plate, and then what we then saw? We saw again strain thinning. Even if the value of strain was larger, it showed that something is happening. Then we made a little bit different situation. We took the material and we made the gelation even in the rheometer, not as a separate cake, but the gel was made in the rheometer. And then we had the smooth plate and again thinning. Then we took cone and plate, thinning. But then we took a cross-hatched and parallel plate, and then we saw a massive strain hardening. So this is the outcome. If we took all the concentrations and then we took the modulus values, don't pay attention so much how we define the modulus, but because there's a certain habit in the literature to analyze the material. But anyway, this is a modulus, and here is a shear stress. We see that in all concentrations, there's a shear hardening. And we saw that in the microscopy that in all cases, the junction number was 3 before the shearing was starting. So it was exactly like I showed in the previous slides, that then upon deformation, this material transformed to above, across the critical coordination number. You remember this. So we first have the coordination number 3, and in deformation, we pass over this value, this border to this rigid value. So in principle, we can somewhat well understand now what happens in the system, but not extremely in depth. So it requires quite much of physics still. And one of the nice things is that Agarose is a strain hardening material which allows a good cultivation medium for biological cells. Let's take then optical properties. So, of polysaccharides. And of course, we all know that what are the classic optical properties of polysaccharides. We know that cellulose nanocrystals make chirally twisting cholesteric liquid crystals, which have structure, color, because of the Bragg reflection of the light. And I point that this is the structure color is due to order. Next, I'm going to talk disorder. So really understand that here is a question of order. And this is also in biology in some berries. Then in some cases, the optical color is a transparency, which is very important, for example, in optical applications. The transparency can be connected with, for example, carbon nanotubes to have transparency and conductivity. And then this is rather interesting. So this is Juan Ginestrosa, who is a professor at Cornell University, and he just wanted to show that plasmonic nanoparticles can be connected with textiles to make unbleaching colors. And these all are his graduate students, girls, who made then a kind of fashion show in New York. And all of these textiles here, they are, the coloring is made of plasmonic nanoparticles. Well, I said that I'm going to describe now disorder. So this animal is a white beetle, and it does not have white pigment, but it has a disordered network which scatters light. You see that the overall theme in this talk is networks. So this is a kind of optical network. And then of course comes question, could white pigments be achieved in this way? Because as I said, titanium dioxide is soon banned. So then what we did with Silvia Vignolini group in Cambridge is that we took, and one point still more, if you see what is the size of these network materials, they are 100 nanometers. So it's rather big. Then if you would like to do similar materials with nanocellulose, nanocellulose is a little bit too thin. But of course, we can turn things upside down because everyone wants to make a well-defined nanocellulose material where the transparency is, for example, achieved. But we wanted to make poorly defined materials with nanocelluloses, where there could be also big and large network pieces. And indeed, then we managed to have something which reminds this white beetle. So let's take first the well-made cellulose nanofiber film. Then here is a transmittance, here is a film thickness. And what we see here is the normal light diffusion. It can be modeled by the Brownian diffusion across the membrane. But in this material, which we intentionally made in a very poor way, then we notice that the transmittance go much more quickly down as a function of thickness than in the normal diffusion. Incidentally, this can be modeled to be so-called anomalous diffusion. Anomalous diffusion is not the normal Brownian diffusion, but this anomalous diffusion is observed in very many living materials. Incidentally, the physics is rather complicated, and it is a kind of, if there are physicists around who know a little bit disordered materials, it could be nice to know that it is a form of Anderson localization, and Anderson localization is a Nobel Prize winning concept for P.W. Anderson for 30 or 40 years ago already. Anyway, here you see that they really have different whiteness. Here is the standard way of making nanocellulose with fine fibrils and with the normal light diffusion, and it is semi-transparent. And here are the materials which have also thicker parts, and then you see that it is much more white. And what is thought is that the importance is here the disordered case, that there are thick fibrils, dense parts, and also so-called also the ballistic photons. Okay. We are trying to make this as a product sooner or later. Then comes a question, could we do it also switchable? Then let's say take a polymer which is thermoresponsive. This is N-isopropyl acrylamide. It's polynipam. The chemical structures here. Here is the temperature, here is the polymer concentration. And what is the property is that at low temperature, it dissolves in water, and at high temperature, it phase segregates. And if it phase segregates, it's a little bit opaque. But it's only a little bit opaque. How to make it more white? Then we have to make more scattering interfaces. And what we did, and why this is connected to polysaccharide, we took Agarose. We take first polynipam covalent gel and Agarose physical gel and made so-called double gel, where both of these materials make a network here in this case. And then we heat the system, and then the Agarose melts, and then it can flow away from the network, and then it just leaves open pores there in the presence of polynipam. And then you see that in this case, the whiteness increases strongly in relation of the pure standard polynipam. So this starts to be rather white. And then I noticed that I skipped something, one slide, because I just want to show still 3 slides more, because I want to go now to optical fibers. So polysaccharide optical fibers could be extremely interesting. And just to remind you why optical fibers in general are interesting. So glass fiber-based optical fibers are used everywhere in the telecommunication. Practically all the long-distance telecommunications and internet is based on optical fibers these days. And what is typical there is that there's a very, very low loss. They carry signal over large distances. That's good. But because they are glass, they are vulnerable for brittleness. And if I would like to make a kind of biosensor, I would not like to have glass in my body because brittle material. Over the years, there have been efforts to make also polymeric optical fibers. So for example, having polymethyl methacrylate core, and then there would be some kind of coating on the material, because there needs to be a total reflection at the interface of the outer layer and the core. So they work, but they are high losses. They work only for small distances. But there are new applications, sensing, lighting, and decoration. But now, just a few years, recent few years have shown that there can be bio-based optical fibers, for example, silk-based optical fibers. I'm now working in Bayreuth University and as a visitor, and for example, here there's a quite big effort to have silk-based optical fibers, for example, by car industry. But what we are interested in is polysaccharide-based optical fibers. If you see, important point here is the refractive indices. And you see that very many of the cellulose or polysaccharides have refractive indices quite close in 1.5. Now, I showed 2 examples how cellulose or cellulose-based optical fibers can be made. So here is Hannes Orema and the others have been making with regenerated cellulose cores and then cellulose acetate outer cladding or coatings. And this works rather well. So the attenuation is first of the fiber strength is rather good. So it means that it is not brittle. Perhaps you could allow this kind of material in your body. The attenuation is rather acceptable. And so it's compatible with polymeric optical fibers in general. And here you see that how light goes there. But you see the problem is that you can't transmit light for kilometers or hundreds, tens of kilometers, but you can transmit light for, let's say, 10 centimeters. But that is enough for medical applications and also for advanced textiles. And what we have been doing is that we have been using methylcellulose, whose refractive index is 1.49. And what we do is that we just pump the methylcellulose water system in ethanol-based coagulation bath, and then we draw the fiber, and the fiber is very transparent. That sounds very good. And then the losses can be even smaller. They can be 1.5 decibel per centimeter, and the present record is still 10 times less. So it develops quite quickly. So, and then here are the stress strain curves, and you see that 150 megapascal is achievable. So I'm coming now to end. Something like 2 minutes over, but perhaps there's time to give still the summary. So strain hardening was the thing what I first described, is very general in macromolecules of living systems. Then we studied very carefully Agarose strain hardening, and we showed that if one wants to have or reveal the strain hardening, one has to avoid the slip. And this is really difficult. And one way is to use roughened plates and in situ gelation. And this is the most gelation. What we think is that if people go back to the old polysaccharide research, one could find that very many new polysaccharides are found to be strain hardening, and in this sense also interesting for the biomedical applications. Sustainable bright whiteness is searched to replace metal oxides, and this can be achieved in nanocelluloses, or in even more generally, I would say, in wood processing using so-called fines, and the physics behind that is based on anomalous diffusion. Then one can make temperature switchable whiteness and coatings if one just adds more scattering interfaces in the system, and there's an Agarose is very good. Then finally, polysaccharide optical fibers are demonstrated, and we think that they are really promising in medical sensing and high-tech textiles. And incidentally, the first demos to combine these two high-tech textiles have already been done in combination of the designers and scientists in our university. So basically, I'm at the end. So I thank ERC and European Union and Academy of Finland, and I would now like to answer your tough questions.
Thank you, Olli. Now the floor is open for question and discussion. You can leave question in the chat. You can also turn on your microphone and ask, or you raise up your hand and we can see you. But now, Olli, we have one question already in the chat, which is from Ying Willem Nol Daily. So the question is strain hardening. Can that be applied to make more stress-resistant super absorbing materials so that the return more water or solute under pressure of body above it? So
I would say that this is a good question. I don't have a good answer. I said that even if we pretend to explain some of the observations what we have been doing. So it has taken 2 years to understand them. And I said that, let's say, having a rational approach for new materials is not so much developed. So I see that that could be a very good functionality. I could have some ideas how it could be done, but I'm not convinced that they can really be done. So,
yeah. Okay, the next question I think is from Pedro. So thank you, Olli, for the very nice lecture. I have a question about your brightness, whiteness system. Usually optical brightness absorb UV light and emit on visible blue. What is the difference between your system and the traditional OB that is optical brightener, right?
It's Felix Plumper. Hello, Felix.
So the question
Hello.
before that, yes.
So that was
from Apnoe Association. I think it's from Pedro.
So there are different ways of there can be absorption, light absorption, and there be light scattering. And for this anomalous scattering is based on the physics behind that is that if there are different length scales of fibrillar materials and pores, then there are numerous scatterings and the scattering events. And then there's light interference at each scattering events. So it's a kind of, let's say, totally messy process, scrambling the light quite much. So this is, I think this is, if I'm not a wood scientist, so let's say, I think that let's say the light absorbers are usually, or the whiteners are light absorbing materials, but they are scattering materials. I'm sorry if the answer is wrong, but let's say this is what I think is the difference.
Yeah. Okay, thanks. And the next question is from Felix, and I heard Felix was speaking. Do you want to?
Okay, I can also address it personally.
Yeah, please.
Yeah, thank you very much. So thanks for the nice results. And I have one question regarding the electron microscopy images you presented, and regarding the connectivity. You showed that you have certain parts where you have a connectivity of free, and I wonder how the samples were prepared and how that connects to the actual state in the rheometer, where maybe things could be different, right? Or am I wrong?
Yes, of course, this is exactly right. So because your question is really proper in the sense that trying to make microscopy so that it really doesn't change the morphology in comparison of the wet samples, we can't be absolutely sure. We made it supercritical drying, and this was best what we could do to kind of, let's say, limit the aggregation. But of course, there's always a danger that this is not exactly the same. But I would still say that if we see in with the supercritical drying, if we see smaller junction numbers than the critical number, then it means that there's less aggregation than if it would be totally catastrophically aggregated. So I would say that it is not possible to make quantitative kind of comparison. So it has to be qualitative.
All right. Thank you very much.
Yeah. Thanks. And Olli, can I ask one question on the last really fascinating example where you have a cellulose-based optical fiber? Can you tell a bit more about the challenges? So for example, did I understand correctly? It is a hydrogel, which is transparent. Thinking about the medical application. And what would be the challenges of thinking about the mechanical strengths? Would it be or stability in different environment and the different ionic strengths? Would that be challenge?
Yeah. So you perhaps a little bit, or I was perhaps not clear enough. The actual final optical fibers, they are not. At least these fibers are not gels; they are solid materials. I would say that so what we can do these days is we can use them as a humidity sensor. There are the VTT people in Helsinki. They can do it. They can even use it for sensing breath and also the movement. If you ask what is the most difficult thing, I would say that the most difficult thing is to connect light sources to the fibers and how to do it so that it is compact, how to make the washing, how to so what I personally think that the most relevant applications will be in the biological application, for example, medical applications, for example, sensing different organs and their situations, because this is exactly kind of proper length scale, because this is a few centimeters and it is enough to make the optical sensing and there's all kinds of optical measurements done in these days. There's optogenetics, whatever. In biomedical, people use catheters, and then I think my guess is that these will be the first applications.
Yeah.
Whether there will be really a kind of, let's say, high-tech textiles, for example, measuring active properties, then there are also other competing techniques, for example, electrical measurements, and not necessarily optical measurements. Then, of course, everyone talks about, let's say, the decorative things. So I think, for example, car industry is interested in making new kinds of decorative lightings in the as far as I understand, in the cars. Whether there could be decorative textiles and which could be kind of attractive for customers, this is a question what we have been posing to our designers. So that, let's say, if they would design fashionable new clothes, we would like to do them, but let's see.
Yeah, okay. Really, impressive and fascinating. Thank you, Olli. And thank you for joining us, and really great that we have this open discussion as well. And now we will move on to next session. Julia, are you there, right?